question 5. This is the one with the biosensors and the enzymes and the equation that probably has thrown you a little bit. So let's go through that question slowly. The first part is literally you are given a graph. You're given a graph and it's telling you that actually the initial rate of reaction, so at that point here right at the bottom, the initial rate of reaction where you can't really draw a line onto it just yet. How straight would it have been? How steep would that line have been? So they have done it for you. They have drawn a tangent for you here to show the initial rate of reaction. If you were to draw a tangent, let's say at 0.60, the tangent would look something like that, okay? So you'd have a shallower gradient at this point, okay? But that is not the question. The question is regarding the gradient here, the tangent there. So use this tangent, use the line that's already drawn in, don't draw another one. Use this tangent, calculate the initial rate of reaction of that enzyme. Express your answer in terms per minute, per minute. Here, have a look. Your scale is in seconds and you're going per minute. So there is a little bit of setting a little trap for you there. Whenever you're doing tangents and you get to pick the X and the Y yourself, do it as big as possible, as wide as you possibly can, because it gets you a bit more of an accurate reading. So let's say that little line is accidentally beautifully drawn for you onto that line. So where you've got 30, follow the line up to here. If you go across, I don't know how straight I have been here, 9.4, I'm kind of getting to, here we go, 9.4. If you're looking at the grid exactly, it's kind of from the 9 line 2 points up. So be precise with your readings. My line across is kind of, yeah, it's a bit wobbly, but here we go. 9.4. That relies on you again. Look at the scale of the y-axis here properly. Each small division is an 0.2 increase. So be specific there. Good. So you've got your y, you've got your x. It is y divided by x. So you've got your y, which is your 9.4 divided by your 30. And then please don't forget your time thing. It wants it per minute. Your numbers are given per second, so you need to add a times 60 for the seconds here. So that is a little bit of a trap there. Again, if you did this right, you got to 18.8 milligrams per minute. Okay, or you do it milligrams times minute to the power of -1. Okay. You can do it with different numbers. Let's say you're doing it with a slightly smaller triangle here, but it may just not be as precise. Mark scheme is here if you wanted to screenshot it or pause it quickly. Right, then the question was, and I'm going to rephrase that question afterwards. Explain why the rate of calculated for the first 30 seconds would be lower than the initial rate. Let's rephrase it. Why is the initial rate higher than if you took an average for the first 30 seconds? What happens in the initial rate to make that initial rate higher? It's higher because you literally, whenever you're forming an enzyme substrate complex, whenever you've got enzyme and substrate, either of them could potentially be limiting, but at the beginning, there doesn't seem to be a limiting by the substrate. So you've literally got glucose en masse, literally lots of it. So that means every single active site on the enzyme is occupied with the glucose to react there. And gradually, as you go through this reaction, gradually glucose and enzymes no longer meet as quickly because the glucose concentration gradually falls, less and less and less glucose around, until eventually you have no more glucose left. That means you can no longer produce any more of the gluconic acid. Here we go. The mark scheme here, where are we? Okay, maximum concentration of glucose at the start, less glucose available as the reaction progresses, and the active sites occupied at the start, and some active sites are vacant as the reaction progresses. Right, getting to the harder parts here. You will always get a question with something that looks completely new and confusing for the sake of how do you deal with something unfamiliar. You will get reactions that look completely, oh my goodness, what on earth is that? So try to approach that as calmly as you can. Part of the mechanism for the conversion of glucose into gluconic acid. So we're going from glucose to a gluconic acid by whatever that is, GOX, okay? That was your compound that was named across here, glucose oxidase, GOX, okay? It's shown by the equation below. It's a two-step equation, and you have got FAD as a cofactor to the enzyme. So let's try to take this to pieces. Glucose reacts with something, makes an in-between product here, the gluconate, and the FAD. You have learned of FAD and FADH. Hold on a second. That is literally something that can be regenerated again. Oh, look, it's regenerated here. The FADH is turning into FAD again. So that cofactor to the enzyme that is helping. So this is here, the enzyme is helping. So this is your enzyme doing the activity. Glucose is reacted to gluconolactone, and that cofactor here being oxidized, and here we're reducing it again to get the FAD back. So a two-step equation suggests the function of FAD. You can call it hydrogen acceptor or electron acceptor. So this is no different at all to how you've had it in the electron transport chain, or when you've had FAD turn to FADH. Where is it? It's happening in the link reaction, in the Krebs cycle, and obviously the regeneration of FAD in the electron transport chain. So that is something that you should be a little bit familiar with. That can just be transporting the hydrogens and electrons. The question following is, one type of glucose biosensors involves the detection of oxygen concentrations in a sample of body fluid. Name 2 body fluids that could be analysed. I've had quite a few of you coming up with saliva. If you open your mouth, the oxygen concentrations will be higher in saliva. If your mouth is shut, as it is overnight mostly, and that explains bad breath in the morning quite a lot, because you've got anaerobes doing a little bit better overnight, okay? So you cannot have saliva as part of it there. It will need to be blood or urine. So you need to have both there for the answer, blood and urine in that one. With reference to the information above. So you need to refer to this here with reference to the information above. Explain how an oxygen electrode, okay, here's oxygen. Okay. Explain how an oxygen electrode could be used to give a quantitative measurement for the glucose concentration. Okay. How can we use the number of oxygen particles? An oxygen electrode would actually give you, or a concentration number for oxygen. How could the number for oxygen give you a measurement for the number of glucose? Those reactions are linked. What you have produced here will be used in step 2. So if there's no glucose around, you won't get the reduced FADH, and which means that that second step won't be happening. Whatever the in-between fancy names and labels are, without this reaction taking place, that means without glucose being present, you won't have the second one being there, and therefore oxygen wouldn't get used up. So what you could have is, if oxygen is lowered, that means glucose is being used up as well. Or if oxygen is being lowered, then this compound is produced. Okay, so if oxygen is lowered, glucose is lowered. If oxygen is lowered, then this product here is increased. That's what needs to be there. Let me just pop over to the mark scheme here a little bit. So the oxygen electrode could detect either the use of or the depletion of oxygen from that second reaction. The number of molecules of oxygen used up in step 2 is proportional to the number of glucose molecules broken down in step 1. So linking those two reactions together, they're saying that, okay, if we can measure oxygen, we can therefore indirectly measure how much glucose was there in the first step. That was a little bit of a disguised question, but could have been done. That could have been done. The last one on this page, but there's another one over leaf. When using a glucose biosensor, explain why it is important to maintain, okay, 3 marks, a constant temperature and the use of a buffer. You've actually got 2 things here and you're getting 3 marks. So one of those 2 needs to be explained a whole lot further. Whenever you hear temperature, it's a bit like earlier, I think it was question 2 where you had the word aerated, or question 3 with the hydroponics one. Aerated automatically means, yeah, is it oxygen, is it carbon dioxide, is it nitrogen, which gas are you talking about? Whenever you hear the word temperature, the automatic link needs to be kinetic energy of particles. Temperature is when particles have a higher kinetic energy, therefore they're colliding more likely, and the whole kind of collision theory argument, those of you who do chemistry will do a touch better, but that is GCSE chemistry. That is very simple. If particles have a higher energy, they're colliding with more intensity, and therefore you'll have more successful reactions. Enzyme activity, you've got 2 arguments. One of them is the temperature argument, and the other one would be the shape of the active site. But for here, literally all you'd need to say, it would affect, okay? You'd have an effect on it, okay? The buffer, you'd need to explain a little bit more, with a bit more detail. A buffer is something that keeps your pH steady. So if there are disturbances to the pH into the higher region, then automatically a buffer would bring it back down. Why is that vital? Why is that important? Look at what you're actually making in your reaction. You're producing an acid. What do acids do to enzymes? You're talking about an enzyme that's doing the whole situation. So hold on a second. If we have an acid present that is being made in the reaction, the acid will automatically change the shape of the enzyme, change the active site. Therefore, your reaction would not run at optimum speed if the active site is maybe not necessarily fully denatured, but it will be changed. So here we go. The change in temperature would affect kinetic energy and result in readings being higher or lower. So just affected would do here. And the second and third both go with the pH level. So the production of gluconic acid would lower the pH. Lowering the pH would change the shapes of active sites, resulting in readings being lower than expected. So that would have been the full argument. Again, I think I've been a bit nice on marking that one here. Last question here, and that was literally, you've got enzyme means you've got a competitive inhibitor. If you're looking at this, looks a bit similar. If it's a bit of a similar shape, then that can potentially match in the active site. So if you're analyzing this properly, experiments have shown that the benzonate can inhibit that enzyme from working properly. Inhibit, that's the word that is avoiding using competitive inhibitor. So actually using the word competitive inhibitor has to be in there. By bonding to the active site instead of the glucose. That's what that already implies. The diagram shows you the arrangements of carbon and oxygen atoms, and using the information provided in part B, so using the information provided over here with the equation, so you're combining this information together. Explain why contamination of a sample with that sodium benzonate would affect the accuracy of the biosensor. So, key idea, similar shapes. Therefore, if we have an enzyme, the benzonate will get into the active site, as it's in a similar shape. It will be a competitive inhibitor to the glucose. The active sites will be busy trying to process benzonate. Obviously can't, therefore, process glucose, what it should do. Therefore, you'd have a slower reaction. Where actually was that enzyme that's being slowed down? Here, that was the enzyme. In that equation, you have that enzyme. So that reaction here would be slowed down. We would have less gluconolactate and the enzyme and NADH formed, so less product formed here. And let me just go through the mark schemes. Probably easiest if I do it that way around. So the change in leave that for last, because that literally is the final argument. That is the final argument of the whole lot. Start thinking of this here. So benzonate has a similar shape to the glucose, therefore it's a competitive inhibitor. Okay, it would occupy the same active site, and therefore you're not going to have the enzyme substrate complex with glucose formed. Therefore, the step 1 of the equation would not work as well. Step 2 of the equation would not work as well. And therefore, the change in oxygen levels would not be detected as well. So the change in this oxygen here would not happen as much. Therefore, because you use the oxygen to predict your glucose levels, Therefore, the oxygen levels would be wrong, which means therefore the impression of what the glucose concentration would be is wrong as well. So there's a change that would be detected differently.